Okay, 20.6, we're finally going to talk about the energetics of these nuclear reactions in a quantitative way. So in an exothermic chemical reaction, the energy that is released comes from the formation of stable chemical bonds. Some bonds are broken and some bonds are formed, and in the end the products have stronger bonds than the reactants, and so energy is released. For nuclear reactions, energy comes off because of the formation of stable nuclei. There are no chemical bonds that are involved, but the attractive forces between the components that make up nuclei can be more or less stable. And when when the nuclear reaction products are more stable, then they release a lot of energy. And that energy loss is so great that it manifests as a loss of mass, according to Einstein's famous equation, E is equal to mc squared, where E is the energy, m is the mass in kilograms, and c is the speed of light. So c, you may recall, is 2.998 times 10 to the 8th meters per second. And the units here make sense because 1 joule of energy is a kilogram meters squared per second squared. And so your mass is in kilograms, and the speed of light is in meters per second squared, and so this is going to give you joules. Okay, so in what way, what do we mean when we say that the energy loss manifests as a lost mass? Well, let me show you. Okay, so if you consider this alpha decay of uranium-238, we can use a mass spectrometer to measure the precise mass of uranium-238 and the precise mass of thorium-234 and the precise mass of helium-4. And you see they're given in that table. And if you add up the mass of thorium and helium, it turns out that they are less than the mass you started with. They're less than the mass of the uranium itself by an amount of 0.00459 grams per mole. So that doesn't look like a lot, and we needed to develop really sophisticated methods to even detect that, but we have mass spectrometers that can measure to enough sig figs that we know that the thorium and helium definitely do way less than the uranium. So where did that mass go? That mass represents the energy that was released. We can sort of change this reaction a little bit. The delta E is equal to the delta mc squared. So the amount of mass that was lost is going to correspond to an amount of energy that was lost. We'll just turn this into kilograms. So that would be 4.59 times 10 to the negative 5th kilograms. And then multiply that by 2.998 times 10 to the 8th meters per second squared. And that's going to give us the energy that is released through this reaction. And it ends up being 4.125 times 10 to the 11th joules per mole, or 4.125 times 10 to the 8th kilojoules per mole. You may or may not have an intuition at this point about how much energy that is. Combustion reactions of high density fuels, really energetic chemical reactions, might lose 1,000 kilojoules per mole. So they'd be exothermic on the order of thousands of kilojoules per mole. And this is 100,000 times more energetic than that. So 100,000 times more energetic than even the most exothermic of chemical reactions. The energetics of nuclear reactions is really in a whole new field when compared to chemical reactions. Also, this is an alpha decay reaction. Uranium decaying to thorium and releasing a helium is alpha decay. If we were to look at fusion and fission, then they're still more energetic than alpha decay. So fusion is about 10 to the 9th kilojoules per mole, but also 1 mole of hydrogen is particularly small mass, and so on a per mass basis, fusion dwarfs this again by about 100,000 times. And then fission is maybe about 100 times more energetic than alpha decay. At any rate, it's tremendous amounts of energy. I want to say that your textbook does what almost everybody does and describes this as mass being converted into energy. And I actually take issue with that. I want to sort of contrast this sort of a reaction with matter-antimatter interactions. So if I have an electron plus a positron, that is going to go to pure energy. The electron and the positron both have mass, but this is matter and this is antimatter. They will annihilate each other, and their mass will be converted to pure energy. There will be no matter left afterward. In the case of the uranium and the thorium and the helium, there are no particles that are eliminated. You have the same number of protons and neutrons and electrons at the end as you had at the beginning. And so I just don't like to talk about this in terms of mass being converted into energy, but rather to say that the uranium was already a composite of mass and energy, and it's the mass that we observe is going to include energy in it. And so what we've lost is energy. And that loss of energy manifests as a loss in the observed mass. Basically, whenever we weigh the mass of something, what we're weighing is both the amount of matter which makes up that thing and the amount of energy of any form that it holds. And so for these fusion and fission reactions, it loses enough energy that the mass that we observe is lower. Anyway, that's maybe a little bit pedantic, and at this point I should just shut up and move on.